All right, so I'll get started. Interrupt me. Obviously, it's a small group, so we can keep it pretty informal.
Should I turn off the light in the front?
Yeah, I think it'll be okay. I teach in here, and people don't usually seem to complain. But if it's hard to see, then we can adjust. So I'll do another session next week where I'll focus more on coding and writing parallel code. And here, the idea is to just give people an overview of what some of the resources are available that are in the department and outside the department. Are you guys both in statistics?
I'm in computational biology.
Okay.
First year PhD.
Okay. And do you have an account in statistics or not?
No.
Okay. Okay. So the Savio stuff may be more relevant for you. Okay. So there's a GitHub repository that has all of this material. There's some demo scripts in here, and also also the slides and some demo code. So I'll put that up here. Okay, so just a comment that we have a bunch of instructions on the SCF website. There are overall instructions for using Savio on the Savio website. And then I also did a couple of tutorials for campus at large on using Savio, and there are links to those here if you're particularly interested in Savio. And then I have some material, some tutorials on the SCF website on doing parallel processing either on a single machine, so on shared memory, or on multiple machines, so in distributed memory across multiple machines. So some of this is based on these various links as well.
What is Savio?
Oh, so Savio is the campus Linux cluster. I'll talk about it a little bit more in a minute. Okay, so just as an outline, I'll talk a little bit about resources on campus, both for doing parallel computation and for storing large amounts of data. And then I'll say a little bit about just sort of terminology of parallelization and parallel hardware. And then I'll talk about how you submit jobs using the Slurm scheduling software on the SCF. And then I'll do the same thing talking about submitting jobs on Savio. And I'll give a little bit of an overview of sort of submitting different kinds of jobs in both of those places. And then, time permitting, I can talk a little bit about data transfer between various places that you might be storing data. Okay, so just to give an idea of what sort of resources we have, on the SCF we've got two different Linux clusters. One of them has about 96 cores, so four machines and 24 CPUs on each machine. And then the older cluster has 8 machines and about 32 CPUs per machine. And you can see they all have a fair amount of RAM on each of the nodes. So in general, you wouldn't be running out of RAM. And we do now have 4 GPUs. There are some people doing some research, or some students particularly in Bin's group, and who had also worked with Joanne, who've been using these GPUs. And they're sort of the 4 GPUs that we own are sort of scattered across the different machines that we have. And there's one that's really for general usage, and the other 3 are to some degree reserved for Bin and Joanne's groups. And then Savio is the campus Linux cluster. It's about 2 or 3 years old, and there are about 330 nodes or machines, and they give about 7,000 cores. Sorry, this is supposed to say 600 cores across 330 nodes. And they provide, there are also, in addition to sort of the general pool of nodes, which have 64 gigs of RAM, there are also some that have a huge amount of memory, up to 512 gigabytes of RAM. There are some that have GPUs, and what else? I think those are the key things. And so the statistics is actually bought into Savio. So we actually now own 2 nodes on Savio that are just regular CPU-based nodes. And Shoran has been using those a little bit. And we own 1 node on Savio that has 4 GPUs on it. So collectively, we have access to about 8 GPUs. So that's getting to be a more powerful resource than we used to have. And so you can either, if you're submitting to jobs on Savio, you can either, you need to get an account on Savio. We can help you do that. And once you have an account, you can either submit jobs via the fact that if you're in the statistics department, because you're a member of the statistics department, or every faculty member on campus gets access to a certain amount of computational time every year. And so if you're working with a faculty member, that faculty member can designate you as a researcher working with them who can use up their resources. So if you use the statistics nodes, you can basically at any one time only use up to 2 or 3 nodes. So 48 cores if you're just using doing a regular CPU based job. So the nice thing about the faculty computing allowance is you can scale up to many, many more nodes at one time. So you could run potentially up to 20 nodes at a time, which is going to be about 500 cores of processing power at any given time. However, anything that you use here in the faculty computing allowance is going to count against the number of computational units that each faculty member is allotted every year. So there are pluses and minuses of sending jobs into different places.
How do we find out how many hours a faculty member has left?
That's a good question. There's probably something on the Savio webpage allowing you to query that, but I don't remember off the top of my head how to do that. And so then the other thing to be aware of is that the National Science Foundation makes a huge amount of resources available for free to people. And so they have this network of supercomputers. So there are many, many different supercomputers or clusters. And you basically apply to get access to it. And there are different ways you can get access through some of the IT folks on campus to just play around a little bit. And then once you do that, you can then apply for what these things are called startup allocations that would give you about something like 50,000 CPU hours. To basically experiment with your code, and that's pretty much, if you apply for that, you're pretty much guaranteed to get it. I think you have to be affiliated with a faculty member, but that is generally not a problem. And then if you really want to scale up from there, if you find out that it's working well for you, you can then apply for these research grants, which are a few pages, and that could allow you to really get a huge amount of computational power. So if doing stuff in the department is not enough, and if doing stuff on Savio is not enough, there are ways you can go even beyond that. So the big picture is, if you feel like you're limited by computing power, you hopefully shouldn't feel that way, and you should just chat with us, and we can see what we can help you get access to. Okay, so a little bit about data storage. So we have about 9 total terabytes on the SCF, and if you ask us, we can often make more space available to you. We just have quotas to try and encourage people not to store files they don't need to be storing anymore. So you could potentially, if you have need for it, have up to tens or hundreds of gigabytes in your home directory, and you could potentially have hundreds or maybe even a terabyte of space on Scratch if you need it and if we're able to free up the space. So that's a decent resource. If you have huge data sets, on Savio, the Scratch space on Savio, there's about 850 terabytes, so almost a petabyte. And it's in some sense unlimited in that there's no quota on it, but as more and more people use it, then all the older files get deleted, and so eventually your old files would get deleted. But in terms of working space, if you had if you had 50 terabytes of data you were working with, you could put it there and work with it on an interactive kind of basis. And then there's this new resource that Savio now provides the ability to basically buy data storage nodes. And so if a faculty member has $7,000 lying around, which is not a huge amount in terms of if they've got a grant, you can basically get 25 terabytes over 5 years for $7,000. So that would store a fair amount of data for a decent chunk of time. And the other thing that some people are not aware of is that we have unlimited storage. As affiliates at Berkeley, we have unlimited storage on Box and also on Google Drive. And the main limitation there is just whether or not you can easily get the stuff onto and off of it. And whether, there are web interfaces where you can do that, but they're sort of clunky if you're trying to transfer large amounts of data. So that's the main limitation with those resources. Okay, so any questions so far?
So is there an interface in the cluster to directly read data from Box or Google Drive?
Yeah, so I'll say a little bit about that at the end. There are some ways to, at the command line, basically transfer between, you can transfer between Savio and Box, and I think you can do basically the same thing between the SCF machines and Box, although I've now forgotten whether I've ever tried that or not before.
But not Google Drive?
Google Drive is a little bit harder to do from the command line. There are sort of third-party applications that are not provided by Google, and I have a link to that at the end. But it's a little bit clunky. If you're really interested in doing it, I could potentially work with you a little bit on it. Okay.
How does Box compare to Dropbox?
It's just another one of these online services, and for whatever reason, campus decided to partner with Box as opposed to partnering with Dropbox, and that's the Box is sort of one of the main providers for campus.
Because Google Drive has this weird idea that when I have like a really huge file and I just change a little bit, it's deleting my file on Google and re-uploading it, which takes forever. And Dropbox has the advantage it can just change basically one line.
Oh, really?
It's much better and much faster.
Oh, that's interesting.
Google.
So that would only work for a text file, presumably.
Also, I'm doing a lot of stuff. I had like basically experiments set up, and I need to change a few lines in a CSV file.
Yeah, right. So if it's a text file, then you could have like diffs and things like that. So that might be possible. If you had a binary file or something like that, then it presumably wouldn't be possible. So maybe Box is just not smart enough to realize that it could do these sorts of things.
Google Drive is not smart enough.
Oh.
Dropbox is.
Oh, Google Drive is not. Okay.
And I wonder whether Box can do it, because that's the reason why I don't like Google Drive.
Okay, yeah, I know that's a good question. I'm not sure about that. Yeah. Okay, so a little bit of the terminology. So I'm going to call every individual processing unit on a computer a core, and then I'm going to call a node. Those are the different computers that together make up a Linux cluster. And then when we're submitting parallel jobs, you can think of it as basically requesting a certain number of processes to run across one or more nodes. And in general, you'd only have one process running on each of the computational units, so that you don't have multiple processes sort of competing with each other and getting in each other's way. And so when you submit a job via Slurm, you're basically submitting a certain number of tasks. And what Slurm means by that is how many processes are going to be running at any given time. So just very, very schematically, you can think of you've got multiple nodes, multiple computers, and they're linked together by a hopefully fast network. And then on each computer, you have multiple CPUs. So maybe there are 24 on a given CPU, and of course those guys are then linked together by an internal network, and they're all sharing memory. And then you've got the same setup on your other nodes. So if you were in this situation and you submitted and requested 2 nodes worth of resources, you could potentially have 48 different tasks running at any given time. And then what I'm going to call computational tasks are usually when we're doing statistical stuff, we often have independent computational tasks that need to get done. So for example, if we're doing cross-validation or bootstrapping, or we're doing a simulation study and we have many, many replicates. So you're going to in general have a big pool of computational tasks that you need to get done. So here's computational task 1. Maybe they take different amounts of time, so I'll use different size circles to sort of indicate that. So you've got a large number of computations that you need to do. And then the question is, how do I arrange things so that I can basically cycle through these 1,000 tasks on in these 24 processes that I have access to. Okay, I think I won't say too much about threading, but threaded processes are basically just processes that use multiple cores. Okay, so on any of these sort of whenever you're working on a cluster that has scheduling software installed, the basic task of the scheduling software and of those of us who set up the software is to try and figure out a way to balance all of the different demands of different users. And so we want to make sure that people are basically able to equally share the resource, or equitably fairly share the resource, but also so that as many CPUs get used at any given time as can be used. And we also try and want to make sure that big jobs that use many, many cores can run instead of just sitting in the queue for a very long time, because there are smaller jobs that keep getting ahead of them. And so those are and also the whole point of the scheduling software is that somebody should be able to submit very, very many jobs and have them queued, and then have the scheduler just work its way through all of those jobs. So those are the different sorts of demands that are being balanced by the software. And basically that is done by setting up various policies to try and make sure that there's this balancing of resources. So one of the things is that there's what's called the fair share policy. So if the cluster is fully occupied and then there are jobs that are queued and waiting, the idea is that your job it's not a first in, first out kind of queue. It's a queue where you put your job in, and if you haven't done much computation recently, your job will probably go to the top of the queue, and it will go above people who submitted earlier than you but who haven't used who have been using the cluster a lot recently. So when you submit a job, you can then look and see where it is in the queue, and in some cases yours may have risen to the top, and in other cases other people's may go to the top above you, depending on how the balancing is going. Once a job is running, they don't get preempted or killed in any way. And so basically once you're in, it should run to completion. So there's not any sort of balancing at the stage of once it's running. But the other thing that's useful to know about Slurm is that the way things can happen in terms of there'll be a queue, and so there might be job 1 in the queue, job 2 in the queue, job 3 in the queue. And Slurm will try and do something that's called backfilling, which is this. So for example, let's suppose this diagram this is time, and these are the number of cores that are available, so this is maybe 1 up through however many there are, 250. And so if there's a user who has a job running and it's going to go for this long, and then there's another user who has a job running and it's going to go for this long. So this is the first job, and this is the second job. And then let's say there are now 3 different users who have submitted jobs that are waiting to run. And I'm going to denote this job with this kind of hatching, and I'll denote this job with this kind of hatching. So this person is first in the queue, and suppose this job needs a fairly large number of cores, and so they might be queued such that the scheduling software is anticipating that this is sort of the slot of core, the set of cores that's going to be slotted into. At this point, if another user is in the queue, and this user actually only requests a smaller number of cores and requests for a short amount of time, such that their job can get slotted in here, such that it doesn't delay the start of any of the jobs that are further up in the queue, then it will backfill this second job in here, and it will run before the first job, even though the queue is set up this way. So the reason for doing that, of course, is we want to make use of the amount of time that these cores are available before this job could even run anyway. So that's another reason that the order of the queue will depend on this fair share policy, and then sometimes jobs that are lower in the queue might start before jobs earlier in the queue. Okay, so let me say a little bit about the SCF clusters. So we have one with 96 cores, we've got one with 256 cores. You can submit from any of the Linux clusters. We're going to start transitioning the older cluster is using scheduling software called SGE. I think some of you have probably used it. We're going to transition that to Slurm in a little while, probably in the next couple months. So in the future, both of our clusters and the Savio cluster will all be using the same scheduling software, so that'll be easier for us to keep track of and easier for users, hopefully, after they make that transition. So one thing to be aware of is on Savio, you have to tell Savio how long your job is going to run for. We don't require that on the SCF clusters, but you could imagine based on this that you can only do that if the scheduling software can only do that if it has some idea of how long the jobs will run for. So it might be the case that in the future we might require people to give time limits, and I haven't really been saying this all that much, but if you are submitting a lot of jobs at a given time to the SCF cluster, it would be helpful to us if you give a time limit to the job. But be conservative about it. Like if you think it's going to run for 2 days, it's fine to say it's going to run for 4 days, just in case it runs a little longer. But even just having that amount of timing information is useful for us.
Is there any way to know that besides just previous experience submitting?
Yeah, I mean, it's basically either previous experience submitting a similar job or doing a little bit of analysis of how things scale in terms of, if you're doing something simple, obviously, and 10 iterations take an hour, and then you can estimate how long 100 takes. Sometimes it doesn't quite work that way, and there's unexpected things that will arise. Yeah. Okay, so the other thing I want to mention, and this is something new that we've been doing on the SCF, and it mimics how things are done on Savio, is we're starting to make use of these things called modules for making software available. And what modules do is basically allow a system to have different versions of the same software installed at the same time, and they also allow a system to have software that might be potentially incompatible with each other installed. So for example, if I type module list on one of the SCF machines, it tells me that I have version 3 of Python loaded. So if I start Python, you can see I'm getting version 3.5.2. And if I want to use Python 2 instead, what I can do is I can do module unload Python, and then module load Python version 2. And now if I start Python, I'm going to get Python version 2.7.12. Okay. So most of the we haven't really set up modules all that fully on the SCF, but we're doing it for Python, and we're also using it to manage people's use of GPUs. And I'll say a little bit more about that in a little while. And you can see what other different software modules that are available with this module avail. I'm not quite sure why it's spitting this out twice, but in any event, this is the stuff that's available on the SCF. There are different versions of Python, and then there's basically software that relates to machine learning and to just using GPUs in general. So the CUDA software is here. So if you're running something on the GPU, you're not going to be able to run it without loading in the relevant modules here, because the system's not going to know where to find the GPU software without having these modules already loaded in.
Is this the same for Savio, or just?
Yeah, even more so for Savio. You basically can't do anything on Savio without loading in a module. Like if you want to run R, you have to load a module to load R, and if you want to run MATLAB, you have to do the same thing. Okay, so then a little bit about submitting jobs. So the basic way that you would that you would submit a job is you would write your actual code, your Python or R or whatever code that is actually going to run the computations, and then in general you would write a small shell script that basically says, how do I run the code, and what are the what are the arguments of the flags for the scheduler, so the scheduler knows how to set up how to run the job. So it's simpler on the SCF because we don't require you to set as many flags as on Savio. So basically, if you want to give your job a name for sort of future reference, you could do that. If you want to set a time limit, you can set a time limit. And then basically all you need to do is just write the shell syntax that will start up your job. So in this case, I have a Python code file called calc.py that does something innocuous. And I'm just saying that all my batch job here is basically just to run the code in that Python file and then spit the output to this file here. So if I wanted to do that on the SCF, I could see. So right now there's not much running on the SCF, the newer SCF cluster. So it looks like Alicia's running a GPU-based job. So I can, so if I look at job-basic.savio-scf, you can see that's just what I had there, what I had in the slides. And I can now do sbatch of that, and that will then submit the job. So now and I'll say a little bit more about monitoring jobs in a second, but now you can see that it lists my job here as running and has a time limit of 3 minutes, and I only requested one CPU for that job, one node and one CPU on that node for the job. You can also do things like SQ-J 20810. So here it said this was the job number of the job that was submitted. So I can say, I could look specifically for that job. In this case, the job's already finished, so I'm not actually seeing it anymore. I'll submit it again. And I can also do SQ and then give my username. Actually, I probably need the quotes. Huh? This is the Slurm one, yeah. So another way to just isolate the jobs are this way. And what that SQ is I have an alias for a particular set of outputs that I want from running the SQ command. So SQ is the general command that shows me what the queue looks like. And I've just tailored it such that I see all of the stuff that I particularly want to see. And I've made a Unix alias for that. So when I just type SQ, that's the information I'm getting here. Is I want to be able to see if somebody's using a GPU. I want to be able to see the time limit, CPUs, nodes, et cetera, et cetera. And so I can see, and also this is some information about the priority level. So that.
So is the default of what everyone sees?
Say it again.
Is that the default of what everyone sees if they run that code?
No, I don't think so. So let's see. I think everyone would just see. I think if you just do SQ, I think what you'll see is just your jobs, and you won't have an S, just a simple letter S, letter Q, because if you haven't defined that alias. Anyway, I wrote that alias in here, and it's in the. So if you did want to put that into your bash RC or something like that, then you could use that as well. Questions so far?
So are we able to see all the all the jobs from every user, or we can see?
Yeah, you can pretty much on any of these systems. So I could, if I do SQ, I'm only seeing my jobs, and there aren't. Oh wait, that's not true. Huh? I guess it is showing all of them. I thought I might be getting confused about which scheduling software I'm thinking about. Okay, that apparently doesn't work. So maybe it must. I guess it's that SQ will show all users' jobs. So if it's busy, you can get a sense of how much stuff is queued, who else is ahead of you, why is it that your job might not be starting, that sort of thing. Okay.
So how busy are these resources in general right now?
Well, if you don't have an SCF account, it's not so relevant to you. The SCF clusters are generally not all that busy. Every so often they'll get busy, and people have to wait for a day or two, but usually they're not too busy. Savio,
Well, it used to be very busy.
It really depends. Yeah.
I was like,
Yeah, but could you use that?
no, there was someone else doing like a whole bunch of.
Yeah, that's true. That's true. I think at some point in the summer or spring there was a few weeks when it was very busy. So it really cycles.
That was terrible. I was like, that's why I switched to Savio. And
Right. Well, if the other command that will show the older cluster is, I have an alias for this QST, and you can see there's actually nothing running on the old cluster right now. So you had hit it at a bad time. So Savio often has resources available. Sometimes it also gets busy. So it just sort of varies. Okay, you can also run stuff interactively. So I can do srun, I have to do this minus pty because you want an interactive terminal session, and then you want to be running, if you want to run a bash shell, then you can do /bin/bash. And this should start a terminal session, and you can see that it's actually running a cluster job because it now gives the name of one of the cluster nodes here. So at this point I could then do whatever I want. I could start a MATLAB session, for example. Actually, I think that's not going to work because, well, it wouldn't work to send the, if you wanted to send the whole MATLAB graphical interface over, you have to also add this -x11 business here. So there's a little bit of syntax to make sure that you can pass graphical windows if you did want to do that in the interactive session.
What does that do?
That just allows you to show if you ran, for example, MATLAB, then the MATLAB itself will be running on the remote machine, but it's then going to display the graphical window on your local laptop.
Is this the software for doing that?
Yeah, X11, you have to have an X11 client software on your laptop, and that's just the software that allows your laptop to communicate with the remote machine and basically display the window.
Gotcha.
Yeah. Okay, so then a little bit about submitting parallel jobs. So once you get into submitting jobs that are going to use more than one core, then you basically have to tell Slurm sort of what's the arrangement of nodes and cores that you want for your job. And so the main flags that you need to tell it are how many nodes do you want to use? And then how many tasks, so how many of these Slurm processes do you want to run on each of the nodes? And then in some cases, you might actually want to use multiple CPUs for a task. So for example, if you were going to fit like 20 different linear regressions, and you wanted to have the linear algebra for doing each linear regression be run in parallel in Python or in MATLAB, you could, for example, have, 20 regression tasks. And each one could then use, for example, 4 CPUs. And so as a result, you would need 80 total CPUs to do this computation. And so if you were going to do something like this, what you would need to do is you would basically need to say, I want 4 CPUs per task, and then you would need to, in some fashion, to say, I want 20 different tasks. And this is a bit of a bad example because you can't, at least on the nodes we have, you can't fit, couldn't do this all on one node. You'd have to split it up across multiple nodes. So for example, we have 24 cores per node, so if you did 4 CPUs per task, you could do 6 tasks on each node. And so that means you would need a little bit over 3 nodes worth to do this particular job. So you would need to say something like 3 nodes, and then 6 tasks per node, and then 4 CPUs per task. So that's the sort of thing you'd need to be providing. So as an example, here's a sort of a simpler example, which is maybe going to be more common, is just you want to just run something in parallel on one node on a certain number of cores in that one node. So here's an example of what you do. You'd say, okay, I want one node, I want 8 tasks per node, and then this is an example if you were going to use the IPython parallel functionality. This basically now says I need to start up a certain number of Python worker processes, and then I'm going to run my IPython code that will do something in parallel across those worker processes. So what I'm doing here is I'm actually making use of a Unix environment variable that when you run a Slurm job is going to be available to you. So I'm basically, so this environment variable is going to be filled in with the number 8 because that's what I requested as the number of tasks. So that gets put into this environment variable, and then your code can now query that environment variable and then tell IPython to start that many worker processes, that many engines.
Why would you not just write 8 in there directly?
Well, that way, this way it's just a little bit more.
Just puts your parameters at the top?
Yeah, it's just a little more programmable, I guess. That you don't need to put in 8 in 2 places. You just put it here, and if you change it here, then it'll automatically respect that down here. And then in other cases, you might use these environment variables actually in your R or your Python or your MATLAB code to control things. And there it's nice because you don't have to change a number in 2 different code files. You just have it automatically get pulled in.
So you put all the environment variables up top here?
Well, these environment variables are filled in automatically by the system. Basically, they're going to be filled in based on what you request here as the resources that you're requesting.
But you could even put in the arbitrary stuff that would be executed in other parts of your code. Like, these aren't keywords for, do you know what I'm saying?
No.
Like, say you wanted a variable that's not like a specifically Slurm task for nodes, but some other thing specific to your code.
Oh yeah, you can define any Unix environment variable here that you want, and then you could use it in your code. Yeah.
Yeah.
This one just happens to be pre-populated by the system.
Yeah.
Yeah. Okay, so I could go ahead and submit that, and so if I do sbatch parallel dash, or I think what was it, job SCF. Okay, now if I do SQ, what you'll see, it's a little bit hard to read because the columns got misaligned, but I put a time limit of 5, and now it says I've got 8 CPUs on one node. And I won't go into this now because it's the sort of thing I'll talk about next week. But if you looked at parallel dash analysis.py, this is basically using this ipy parallel package, and it's then it's basically then taking this function f and applying that function f in parallel across a whole bunch of different small data sets to do, I'm forgetting exactly what, do some linear regression on some stratified data set. Okay, so this would be sort of the standard thing that you do, is you know that you want to run use a certain number of cores on one node, and so this would be the basic syntax for doing that. Okay, so then getting to this idea that in some cases you might actually want to use those environment variables in your actual Python or R or MATLAB code. I just have the basic syntax of how you pull an environment variable into different pieces of different software here. So in Python it's 2 lines, in R and MATLAB it's 1 line. Pretty straightforward. Usually you need to cast. Usually it comes in as a character string, and you need to cast it to a numeric value in order to then make use of it. But the environment variables that Slurm provides there are more than just these, but it'll tell you how many total tasks will be in that environment variable. It'll tell you how many tasks there are in each node. It'll tell you how many CPUs there are for each task. how many nodes. It'll even tell you the names of the different nodes that are assigned to your job. So all of these could potentially be useful in terms of writing code that where you can sort of control how you're doing the parallelization. Okay. And then is anybody interested in running GPU jobs, or, yeah, okay. So the usual way that you do this in Slurm, and it's similar syntax, somewhat similar syntax on Savio, is we've set things up so that you have to submit it to what's called a different partition. And so basically what we've done, and this is very recent, is we have these 4 nodes. Good thing you guys are staying close since this marker is running out. This one's better. That's better. We have these 4 nodes, and on one of them we have a GPU. So we basically partitioned the node into 2 pieces. There are 2 CPUs that are associated with the GPU, and then 22 CPUs that are just associated with the other part of the node. And then we have, so this is on SCF SM20. And so if you want to run a GPU job, you basically have to say, I want the GPU partition, which means I want sort of this little chunk of that particular node. And then you need to say, oh, and I actually want to use a GPU for my job. So together that should make available that should make the GPU available to you. And then we're asking that you say specifically what node. So this is the node. The name of the virtual node that has the GPU on it is SCF SM20-GPU. That's this little partition. That's this little chunk of CPUs and the associated GPU there. So that's those are additional flags you need to pass if you're going to run a GPU job on the SCF. And then, in general, people who have been using GPUs have been using various machine learning software. So you then need to basically load in the associated software that you're going to use. So something like TensorFlow or Caffe or something like that are all available. Okay, so I was going to turn and talk a little bit about Savio. So how many of you have a Savio account? I know you do. You do. Okay. So have you successfully logged on?
Since getting an account, have not once needed to use it. So,
Okay.
so no, but I haven't tried.
Okay. So the basic story on Savio is it uses these one-time passwords, which are a little bit of a pain, but there's fairly good documentation about how to set up the one-time passwords, and you basically do it with an app on your phone called Google Authenticator. So basically what you end up doing is you're going to SSH into Savio, and this is the URL for Savio. And then you first have to enter the digits of your sort of static password or your PIN, and then you need to then subsequently enter the digits that are provided by the one-time password program.
I find it ridiculous.
All right, I'll let you take it up with the systems administrators. They'll have a whole security argument for you. So now I'm entering the one-time part of the password, and that should then get me on. So now I'm logged on, and this is a Linux system, just like the SCF machines. Okay. If you do want to pass any graphical windows back, you should add the -y flag when you SSH in.
If I wanted what?
If you want to pass any graphical windows back to your local machine, then you need the -y flag. So Savio, like I mentioned, makes even more extensive use of modules than does the SCF. So if you say module, so if you, for example, if you say which R to see if R is available, you can't even run R without loading a module. So this will not work. On the other hand, if you can do module avail, and that tells you what's available, and you can see that things like R and Julia and various versions of Python are all available through the module system, as well as various utilities up here. There's MATLAB up here. I guess you have to load Git itself, so there's lots of stuff that you have to load.
What's the difference between these?
Yeah, for some reason they decided these were languages and these were tools. I don't know why MATLAB's a tool and Python is a language. I mean, yeah, but it's slightly arbitrary. But
You don't have to load Git actually.
oh, you don't? No, which Git? Yeah, so there must be some extra stuff that comes with the Git module that's not directly available just via Git. But yeah, it looks like you can run Git without loading that module. And the thing to keep in mind if you're running some Python and R in particular in Savio is They have installed a bunch of R and Python packages, but you can't actually see them here unless you first load the R or the Python module, and it's sort of a nested hierarchical structure. So if you do module load Python, I'll do 2.7.8 because that's sort of more standard than and newer than 2.6.6. And now if I do module avail, I should see that there are a whole bunch of Python packages also available that I wasn't seeing before. So NumPy, scikit-learn, SciPy, all of the sort of standard numerical Python packages are now available.
Can you load your, like, if there is a package in R, for example, that I want to use that isn't there?
Yeah, so the basic way to do things is, and it's a little bit iterative, is usually if you for example installed an R package that has as a dependency something that is available on the system, you'll then start installing your own version of it. So you might sort of iteratively figure out what are the packages already available on the system that are dependencies of the package I want to install. Make sure you've done module load of those, and then in R you can just do install.packages.
Okay, so if, that makes sense.
So
like it'll yell if you're trying to, if you have packages that dependencies already exist, but you haven't loaded them.
in R it will probably just try and directly install all of them, which is a bit of a pain because like ggplot2 is a dependency of a lot of things, and it's on the system. But if you haven't loaded it in, then when you load package XYZ, you might install your own version of ggplot2.
I see, and that's not okay.
It's okay. It's just a little bit tedious because now you've got your own copy and the system copy. But
Okay.
it is
That
perfectly
makes
fine.
sense.
Yeah. So yeah, in R you can do install.packages. It may ask you where to write the packages to so that you have control over it, but that usually is fairly straightforward. And in Python you can usually do something like pip install, I think it's -- local, or it might be -- user, and then the name of the package that you want to install. And I like to, oftentimes I'm going to install something that depends on NumPy, so what I'll do is I'll first load NumPy, and then I'll do this pip install so that pip knows that NumPy is actually already available and it doesn't need to install NumPy before it installs the package that I'm trying to install.
Is it possible that I, per default, load R each time?
Oh yeah, you could put that, you should be able to put that in your bashrc file.
Bash RC file?
Yeah. Are you using bash or Tish, or what shell are you using?
Or I can just bash RC.
Yeah, so I think you can do, so this is my bashrc, there's not all that much in it, but you should be able to just put module load XYZ, whatever you want in here.
And the local install packages will eventually be deleted.
No, they'll get installed into your home directory. So there's a distinction between, so if I look, I can see this is my home directory, and this is all the stuff in my home directory, but I also have space on Scratch, and that is here, and so that's a separate file space for files. So the stuff in your home directory is backed up. It's only like 10, you only have a 10 gigabyte quota, whereas Scratch is not backed up, but it's much larger, and you can put more stuff there.
How do I get to Scratch?
Oh, just do cd global Scratch and then your username. Yeah. So see if we can get to yours. See if I can get to yours. No, permission denied. Good. And the other thing is that if you're running jobs where you're reading and writing to disk, then they want you to put stuff on Scratch. Because first of all, it's fast to load it from Scratch, and second of all, if you load it from your home directory and other people are doing the same thing, you're going to be competing for a certain amount of bandwidth going back and forth to the home directories, and that is going to slow everybody's job down. So you want to put any data that you're loading in, and you want to write any output to Scratch, and then after that, if you want to, you could then copy it to your home directory.
So this will speed up my jobs. And I do a lot of writing and free.
I don't know if it'll actually speed stuff up. I did a test and it didn't seem to make much difference, but they do want you to do it because otherwise you're competing for a limited amount of bandwidth with other people, and it's really set up to read and write from Scratch. Okay, so a little bit about submitting jobs. So I said before that you could potentially have access, yeah?
If you put it on Scratch, doesn't that use bandwidth anyway?
But it's just the one-time cost of copying it over there.
Oh, okay.
So the idea is you might be reading and writing you might be reading from that data set multiple times if you're running a job over and over again, that sort of thing. So if when you're on Savio, unlike on the SCF, it gets more complicated in terms of accounts and what you're being charged for. So potentially, if you're in statistics, you could either submit a job through the statistics condo, the statistics nodes that we bought, or you could potentially submit through a faculty computing allowance of your advisor. And so this is an example of what's accessible to me. So I can either submit to the CO stat account, or I have a faculty computing allowance, and so I could submit to that. And then the other thing is, in CO stat, I have access to two particular partitions. So these are groups of nodes. So Savio 2 is just the big pool of regular nodes, and Savio 2 GPU is the pool of GPU nodes, of which we own one of them. And you can see, if you scan over here, it says normal over here. And what that means is you have regular access. I, in this particular case, or actually anybody who's affiliated with statistics, has regular access to these two pools. These other pools, like the pool of big memory nodes and the pool of the older Savio nodes, it says low priority here, and what that means is we didn't buy any of those nodes, so we can only use them at low priority, and in that case, our job could actually get killed by somebody else's job who needs to use that pool of resources. Whereas if you're using a faculty computing allowance, then all of these different pools of resources are available at normal priority. So that's something to keep in mind. Is you have basically, when you're submitting to Savio, you basically have to say both what account, so this would be if you have a condo or you're using a faculty computing allowance, and then the partition is the kind of nodes that you want to use. And if you're just doing running regular jobs, then this would usually be Savio 2, but it could be GPU or big memory, or if you, it's cheaper to run on the older nodes, so if you wanted to save a little bit of money and it didn't slow your job down too much, you could just say equal Savio here, and those are going to be the older, somewhat slower nodes. And so this is basically what a submission script would look like on Savio. It's a little bit more extensive than what I showed you for SCF because you have to include the account and the partition, and they require you to include the time limit as well here. But then after that, the stuff that's not in comments, is the same sort of thing that you would have written to submit something.
If you include a time limit, is your job killed?
Yeah, totally cut off. So the sort of trade-offs here are, if you're too optimistic about how long it'll take, it could get killed and you lose everything if you haven't saved stuff on an interim basis as your job isn't running. On the other hand, if you're too conservative and you say, it's going to run I need 6 days even though it'll only take a day, your job is not going to start as quickly because it's going to get a lower priority because it has to take longer. And in fact, actually, if you're submitting to a faculty computer allowance, the time limit is 3 days. No jobs can run longer than that. If you submit to the stat condo, I think at the moment, because not many people are using it, I don't think we have any time limit. So if I notice that Soren's job is running for 3 months, I'll complain about it. Okay. And then basically monitoring jobs on Savio is pretty similar to doing it on the SCF. There's also this wall command that will show how much memory and how much CPU your job is using, which can be kind of handy to get a sense for that. So on Savio, if I do SQ, we can see there are a lot of jobs from a lot of different users that are running. Some of them are running just on one node, for example, these guys here. Some of them, this person is using 4 nodes, this person is using 7 nodes, et cetera, et cetera. So, and then you can also see that there are a number of jobs that are pending, that are in the queue, that are waiting for resources to become available. And you can also run interactive jobs on Savio as well with sort of similar syntaxes to what I used before. This is sort of an abbreviated version of those same flags. So this is the account, this is the partition, the pool of nodes that you want to use, this is how many nodes you want to use, and then this is the time limit. Okay, and then the same sort of thing that you can basically ask for a certain number of nodes, you can ask for a certain number of tasks, or you could ask for a certain number of tasks per node and a certain number of CPUs per task. And so this is an example of using IPython's parallel functionality across multiple nodes. So one of the nice things about IPython parallel is you can run it on one node, or you can do parallelization of independent computational tasks across multiple nodes. And so what I'm doing here is I'm loading in the various modules I need, including Python itself, and then I'm going to use the pandas package, and I'm going to use IPython. And then this whole business here is basically the syntax you need to start up one worker engine for every core that I requested. So in this case, I've requested 48 different tasks. So when I do this srun command here, it's basically going to start up one of these IPython computational engines. It's going to start one of these for every one of these tasks. And so it'll start 48 collectively across the 2 nodes that I'm requesting here. And I guess implicitly, I didn't even say that I was requesting 2 nodes here. It's just implicit in the fact that I requested 48 total tasks, and each node has 24 cores each node has 24 cores. Okay, so same business. You can use the same kinds of environment variables on Savio as I discussed for the SCF. And then I think I'll mention slightly more about the low priority queue. So the one reason that you might use the low priority queue is it doesn't count against any quotas. The downside is your job could get killed arbitrarily at any time. But it does allow you to sort of burst beyond the resources that we've purchased for statistics. So you could potentially run on up to 20 nodes. You can do the same thing. You can also run on up to 20 nodes in the faculty compute allowance, except you're going to get charged for it. So here, if Savio is not too busy, you could potentially run a very large job for free, basically, by submitting to the low priority queue. And so that would basically involve submitting it under the stat condo account, submitting to the pool or partition of nodes that you're interested in, and then submitting under using the low priority, what's called the QoS. And that's basically sort of the priority status that you're requesting for the job. Okay, so there's a little bit of syntax here for running GPU jobs. Again, you have to submit to the pool of GPU nodes. So that's the partition, and just like on the SCF, you have to actually request usage of a GPU with this syntax here. And then, is anybody interested in using Spark? I could say something about it, yeah. Okay, so you can use Spark on Savio. The difference between, if you know anything about Spark, Spark in general uses something called the Hadoop distributed file system to basically split up your data across the local disk on multiple nodes. So that's how it would run if you were working at Google or if you were doing things on Amazon EC2. If you're running on Savio, it doesn't actually set up the Hadoop distributed file system. It just reads stuff directly off of Scratch. So in some ways, it's actually simpler. So you can basically just submit a job by requesting a certain number of nodes. So suppose I wanted to use 8 nodes, and I'm going to use my faculty computing allowance because I can't use as many as 8 nodes under the stat condo. And then there's a sort of a helper script that sets up Spark for you. So you need to load in the Java module, the Spark module, and then you need to start Spark with this helper script. Or you need to sort of set it up with this helper script, and then you need to start it with this command. And then you submit your job using this Spark submit. And so then what analysis.py has is it has all of the Python code for running the Spark job. So in this case, the only thing, I don't even know if I wrote this or not, but here's an example of just how you would read data in off of Scratch in PySpark. So you basically run the text file method, and then this is going to pull in all of the data from all of the tab-separated files in this particular set of directory and set of subdirectories. And that will read it into one huge RDD or data set that I'm calling lines here. So it's actually it's pretty straightforward to use on Savio because you basically just put your data on Scratch, and then you can just start up PySpark pretty easily.
What is Scratch physically?
It's just some big pool of disks. And it's I don't even remember off the top of my head. Supposedly it's set up so it's very fast to read and write from it, but I don't know. Yeah, I don't know. I don't know whether it's rated or I don't know exactly how it's set up. Yeah, there might be a little more detail on the Savio webpage. Okay. Well, I think maybe I'll save the data transfer stuff till next time. I don't have too much to say here, but I was going to illustrate using this cool tool called Globus, but I think I'll do that at the start of next week. So are there any other questions that people had?
So with using Spark, is there a limit about how much space or storage you use?
Yeah, I mean, officially, the scratch space is unlimited. I don't know if you tried to put,
Yeah, but when you use Sparse, you kind of need the memory to store all the.
well, so right, so Spark is going to operate most successfully if across all of the nodes that you're using, the memory, the collective memory across those nodes is enough to hold all of the data that you want to load in. It will handle it if you can't fit everything in memory. It'll just read in pieces at a time as you process through it. But ideally, you would be able to read it all into memory. So the idea is if you had 8 nodes and if there are 64 gigabytes of RAM per node, so that's about 480, 500 gigabytes of RAM. So potentially you could read in up to that amount of data and have it all fit in memory at once. Of course, then if you start doing manipulations on it and producing new sub-data sets, then you might run out of memory and then it might start reading and writing to disk. But hopefully it would still do that in a fairly efficient manner. I don't know, if you put some really huge amount of data on Scratch, you would probably fill up Scratch and you would get them telling you that that's not kosher. So it's in that sort of gray zone of there's officially no limit, but obviously in practice there is some limit to how much you could actually use. But I think for most people in statistics, we're not using such huge data sets that you'd run into that. Any other questions? Okay.
Thanks, Chris.
Sure.